A volcanic eruption is the Earth's primary method for recycling its interior, expelling molten rock, trapped gases, and fragments from a subterranean vent. On one extreme, we see effusive eruptions. These consist of fluid lava that oozes from the ground to pave new landscapes in thick, slow-moving sheets. These events can be strangely rhythmic. The magma behaves like a heavy liquid, fountaining steadily from vents and flowing downhill in predictable channels. The explosive extreme is a study in raw destruction. These eruptions produce massive columns of scorching ash and rock fragments that rise miles into the atmosphere and obliterate everything in their path. Both events are born from the exact same subterranean mechanism, yet they yield results that appear to belong to different worlds. The surface terrain and the shape of the mountain offer no explanation for this variance. The answer is found within the microscopic chemistry of the magma itself. Magma originates in the upper mantle, where the heat generated by the decay of radioactive elements causes the surrounding rock to melt. Because this melted rock is lighter than the solid material around it, the magma rises buoyantly through the crust, eventually pooling in shallow chambers. The behavior of this magma is governed by viscosity, the internal friction that determines how much a fluid resists flowing. Viscosity is dictated by silica tetrahedrons, the melt's atomic building blocks. Low silica magma has simple structures that easily slide past one another, remaining highly fluid. High silica concentrations force tetrahedrons to link into tangled molecular webs, creating thick, sticky magma. Silica concentration determines the magma's physical thickness, setting the conditions for the resulting eruption style. Within the silica matrix, we find the second variable, volatile gases like water vapor. Under extreme pressure, these gases remain seamlessly dissolved within the liquid rock. Like opening a soda bottle, dropping pressure causes gases to exsolve. In low silica magma, expanding gas bubbles encounter almost no resistance. They move freely through the fluid rock, rising to the surface and popping harmlessly. This steady venting results in quiet, effusive lava flows. Conversely, inside high silica magma, expanding gases are blocked by the tangled molecular web. The bubbles swell, unable to escape the sticky, rigid structure. The trapped gases build internal pressure until the outward force overcomes the structural integrity of the surrounding rock. When that limit is reached, the sudden release of pressure pulverizes the magma into billions of shards, creating a violent cloud of ash and pumice. An explosion is the direct result of gas pressure being forcibly contained by microscopic silica chains. These different chemical reactions leave behind distinct, permanent features on the Earth's surface. Effusive eruptions act as construction mechanisms. By paving over the terrain in thin layers, they build massive shield volcanoes and islands over thousands of years. Explosive eruptions move material in the opposite direction. When billions of tons of shattered rock are suddenly evacuated, the mountains collapse inward to form massive calderas, like the 6-mile-wide basin at Crater Lake. This process follows a predictable physical equation. The outcome of any eruption is determined by the ratio of silica and gas locked within the crust. The tension between molecular chains and trapped gases defines the specific landforms that emerge from the crust.